Okay, good morning, everyone. My name is Dr. Hui from Material Science Engineering at Busan National University in South Korea. So in today's presentation, I'm going to introduce our recent research related to fuel cell. It's mainly bimetallic palladium, platinum, graphene aerogel on nickel form. It's a porous three-dimensional network electrodes as binder-free electrode for electro-oxidation of ethanol. So what we are going to do is we make three-dimensional graphene aerogel and we coating some catalyst as a bimetallic. And we want to reduce the ethanol to generate some electricity for military application in Samsung. So in this talk, I will briefly talk about the current status of fuel cell technology, different type, and the challenge of direct ethanol fuel cells. And we will mention in this study about the palladium, platinum, green synthesis. We are using long-toxic reducing agent and vitamin C, and how we form the graphene aerogel from graphene oxide, and we characterize the performance. So as you can see here, roughly we have six types of fuel cell technology. The first one is proton extreme membrane fuel cell. This is high cost and operation temperature is around 80 degrees Celsius. And the second one is direct ethanol alcohol fuel cell developed by NASA in 1990. We also have phosphoric acid fuel cell, but this one have relative low efficiency at this moment. We have the molten carbonate fuel cell, but we need the carbon dioxide injection at cathode. So we also have solid oxide fuel cell, alkaline fuel cell, but they have different specification for application. For example, this one is high energy density at high temperature operations. And in this talk, we are mainly focusing on direct methanol fuel cell or ethanol fuel cell because this would be the most promising technology for portable and transportation requirement due to its lightweight for portable applications, and this is already applied in the automobiles like the Q-Bate 3. And the advantage compared to existing one could be we don't need the reformer, so we can directly convert the alcohol to energy. So especially if you are using platinum. Platinum is nowadays the commercial catalyst because of high performance. And you can have quite a decent range of the working condition to give the electricity and water as byproduct. So this is environmental friendly. So we don't have exhaust emissions like carbon oxide. And this one is inexpensive because the ethanol can come from bio-waste or renewable energy source. So we have high energy density, easily transport and store. And you can think about the refuel, it takes a minute compared to charging a battery. So you can just simply replace the ethanol fuel cell, the source, and efficiency is around 80%. So if you look at the schematic diagram here, you probably know what we need is we put the fuel like methanol, ethanol, all kind of alcohol, and in the anode, and go through the chemical reactions. The alcohol was oxidized to carbon dioxide and generate the hydrogen, ion, and electrons go through the external circuit. And in cathode side, we use the oxygen from air, and we go through the reductions, so it become water. So in this overall reaction, you have the alcohol with oxygen, and you produce the carbon dioxide and water as byproducts, as well as you generate the electricity. So as you can see here, so our research is mainly focusing on the anode material, but a lot of research is working on the membrane here or cathode here. So the fuel cell market is going to big. For example, is expected to get 5.2 billion in 2019. And nowadays, Japan and Korea are major countries driving the market because we have some needs, and maybe a lot of the membrane is done by LG Chemical, and we have some material synthesis. So, and you can see the big market, as I mentioned, this one is for portable and transportation. So the big market nowadays is expensive because of catalyst is platinum. So the big market would be the military. So like US, they already have ultracell. They generate 50 watt, 55 watt. And you also have another FSC Energy, 1 million from US project. And in Korea, Samsung, they try to demonstrate 1,800 watts for the Korea military in 2014. And you can see that would be the coming technology for driving the, let's say, portable radio devices and some portable electronics. So for the transportation, is also worldwide invest. For example, like GM, Nissan, BMW, and the power stations, like that kind of company, and portable electronic device. So look for the background. So what kind of available catalyst is mainly for the fuel cell? Probably have 3 types. The first one is noble metal, like platinum, palladium, ruthenium, but they are very expensive. However, they have a really good performance. And you can also use some microcyclic complex, like transition metal. You have a transition metal here and some complex. But nowadays, many research is trying to improve the efficiency, but still very low. You also have MSI. This is biofuel cells. So, for example, a lot of research has been devoted to long mobile catalyst space like nickel. They show the catalytic activity. They show the catalytic activity here, and however, they have poor conduction in their nickel oxyhydride state. Therefore, they have much lower performance. The solution is to put the catalyst on some highly conducting carbon-based like carbon nanotube, so they can have the catalyst around the carbon nanotube to enhance the catalytic active site for reactions. So a lot of research has been done, for example, making on hollow sphere, carbon nanotube, or carbon membrane, that kind of things. But the thing is, even this is cheap, low cost, but you can see here the peak current density is really low. It's milliampere per centimeter. So non-noble-based catalyst is still quite low. And later I will show you for platinum-based much higher, almost 200, 300% higher. So now the challenge in platinum-based catalyst is high cost, slow reaction kinetics, because due to the self-poisoning of platinum in the intermediate state of oxidation due to the incomplete reaction generate the carbon monoxide, which reduce the active surface area. And nowadays, the most reported catalysts are support on 2D graphene nanosheets because graphene is an emerging material, have high performance, electrical, mechanical, high surface area, that kind of thing. So a lot of research has been working on platinum-based alloy nanomaterials such as platinum, palladium, ruthenium, iron, cobalt, nickel. And up to now, platinum palladium is the most promising catalyst because of the high performance. And in this talk, we are using this one because actually we work on a lot. We work on platinum, palladium, nickel-based, but we find that this is the best. So, and the catalytic performance depend on the size, the shape, the alloy composition, that kind of thing. So, and the other part, the challenge of carbon support is we need to have high conductivities, high stability, high surface area. So nowadays, the commonly used carbon support is carbon black for commercial carbon black. For research, it's using nanotube, fiber, 2D graphene nanosheets, but they all have one problem is that kind of carbon support, they will aggregate in the synthesis, so they reduce the surface area, aggregate together. And finally, the catalyst, what we saw here, they will go through a organic process, a binder process to cool on the electrodes. So that will lose the surface area. And for 2D graphene, this is the latest promising carbon support because high surface area, really thin, and you can load a lot of catalysts on the functional group here, and high stability and fast electron transport. But the drawback is, even you are using two-dimensional graphene sheets, you have one drawback is you can see agglomeration. So the surface would be agglomerate together, so reduce the active surface area. So for example, this is graphene 2D single sheet. If you make as low with the catalyst, let's say manganese oxide, cobalt oxide, you can see that some surface area was aggregate, reduced. So the method to reduce the drawback is go through the aerogel. From here you can see it's highly porous structures. You have the micropore, mesopore, and really high surface area to load the catalyst. Instead of loading the catalyst in two-dimensional, we put the catalyst in three-dimensional skeletons. And this can maximize the surface area. So how can we do this one? Okay. So we will go through the same method, modified Hummer method, where we make the graphene oxide. This is graphene oxide with a lot of functional group here. And we go through the hydrothermal. So go through the hydrothermal, the electrostatic attraction will stack the graphene sheet individual to a three-dimensional structure. So we can obtain we can obtain a hydrogel. Hydrogel, most consists of water and graphene oxide, reduced graphene oxide. After you freeze dries, minus 80 degrees Celsius, you can get a well-structured porous graphene aerogel. So in this method, what is the novel? The novel is we are using the green method to make the catalyst without using non-toxic reducing agents. So we go through the graphene oxide. We put the catalyst precursor like palladium, platinum, and we use a vitamin C as a non-toxic reducing agent. So we can form the metallic particle here. And this is our another study. We already filed a Korean patent on this one. So mostly the key is vitamin. In this study, we select several types of electrode. For example, you can see here, this is by XRF analysis. We have palladium, platinum with different mole ratio, 1:1, 2:1, 3:1. And we have the atomic ratio. So we will label as PD1, PT2.9 for same ratio for half platinum. In this experiment, we are changing the platinum ratio only. We keep the palladium same because we want to lower the platinum usage. Platinum is expensive, so we want to lower the platinum usage. And you can see in the later, we will label the electrode as this one, PD1, PT2.9, PD1, PT1.31, PT1, PT1.03 as the atomic ratios. So this is what we get. We have a nickel form, it's a current collector, and we coat the graphene aerogel on the nickel form. And from the SCM, you can see that we have some catalyst inside, outside, and this is the EDAS. So we have platinum and palladium. But this sample is here, 1 and 2.9. So which means the molar ratio is here, 2.9 is 1:1. So 1 palladium and 1 platinum molar ratio, and we get PD1 and PT2.9. So from here, what you can see is the platinum have higher atomic weight percentage detached, and the reason is if you put 1 to 1 molar ratio, due to the reducing potential of platinum is much higher than palladium. That means more platinum will form, even 1 to 1 molar ratio. So that's why we change different molar ratio, and we finally find that with much platinum molar ratio, the nanoparticle gluon will be much smaller because the reduction, we have less precursor concentration here, and we can control the particle size, and which is very important for the performance. So from here you can see this is 1 to 1 molar ratio, 2 to 1, and 3 to 1, and maybe not very good at SEM. So roughly we can see the distribution of nanoparticle is getting smaller. It's getting smaller. So for example, this is 1,000 and getting smaller. So if you look at the comparison, you can see the range from 250 to 1 micron to 800 nanometer and 1.7 micron. And then this is the mean, the FH diameter of the nanoparticle. And from the XRF, we can see the material loading. So we use the XRF to analyze the metal weight percentage. So you can see with less platinum, we get less weight percentage loading. 9 point something is reasonable, because if you have more loading, the performance will be better, but 10 is roughly for the characterizations. And so depend on the, because of different molar ratio, the size is decreased due to the nucleation rate of platinum in the composite, in the alloy. So we look at the XRD, you can see the XRD is follow the JCPDS cut number here, and the peak 111, 200, 220, 311 of platinum and palladium are very close. So basically, they are just 0.1 degree angle. So they are close here. But if you look at the high resolution here, I would say the platinum is around 39 and palladium is around 40. So we change the different ratio, we form the alloy, and the peak is within the range. So that means we have the alloy conditions. And from the XPS, we can see that, for example, this is the graphene oxide. You have some oxidation group here, but after reductions, we can see the oxidation peak. For example, this peak is much smaller, so we can claim that this is reduced graphene oxides. And this is very typical. We have the platinum and palladium different valence state. And this is the performance. So what we are going to do is add, sorry. Okay. Here? Okay. Got it. Thank you. So what we are going to do is the electrocatalytic study. This is cyclic voltammetric diagram. Simply tell if you give the potential, what happens about the chemical redox reaction. So from here, the black one is PD1, PD2.9. So we have the oxidation peak here. That means we oxidize the ethanol. And we go back, and here's reduction peak. That means the catalyst reduce back to the catalyst. And from here, you can see this one. Molar ratio 3 to 1 give the highest current density, which means more electron will come out, go through the reactions. And for example, I already labeled here. So you get, we have per gram. We divide the current with the active loading mass. So this is 324, is the highest current density, and this is second and lower. So the higher density is due to the size is small, so higher active surface area. And this ratio, the forward current density and backward current density ratio means the poisoning tolerance. So if you look at the reference, For platinum, it's around 1.2, which means platinum is easy to be poisoned by the intermediate state, and palladium is much better. So we, in the alloy, we can achieve much better performance. And the onset potential is so here. Onset potential means the onset to have the reductions, oxidation. So you can see here, this one is the 2.9, PD1, PT 2.9, and red color is 1 and 1.31. So we have much, we have much negative potential here. Maybe some mistake, right? Okay. So I think the label got some mistake. So anyway, you can see here the onset potential is more negative. So as I mentioned in the before, this is a fuel cell. The voltage range is due to the positive potential minus negative potential. So we will have a higher voltage range. And this one also tell about the kinetic, about the ethanol oxidation reductions. And the reason is due to much more active metallic orientation surface compared to platinum or palladium, because the alloy, they have more orientation surface. Okay, it's not working. Why? Okay. So we will look at the stability. So usually we have cycling number. You can see from 0 to 1,500 is a decent cycling to evaluate the performance. So in previous study, the performance was recorded at 30. That means all the performance is at 30, because after 30 to 150, the cyclic Voltam diagram is similar, so not much change, so that is already stable. So from here you can see, if we look at the current density, at the beginning is increasing high and then up to here stable. So, but after you keep going the cycling, the current density decreased because the surface was utilized, go through the reaction, so the active surface site decrease, so therefore the performance will be decreased. This is the general trend. And from here you can see that palladium to platinum 3:1 molar ratio gives the highest performance compared to the other concentration range. And the IF over ID is the poisoning tolerance, so which tell how stable is the catalyst. And from here you can probably see that the PD1 to PD1.03 is more tolerance, more stable compared to the other two alloys. And this one is the onset potential. Onset potential is more negative. For example, here, the first cycle is minus 0.62, but after 1,500 cycle, it's become more positive. That is natural because the catalyst is degrade for long cycling. So from this study, we can see that for this alloy, composition is much more stable compared to the other. We also carry out, actually we have the other data but didn't present here. We compare the platinum, and palladium. They are much lower here. So alloy is much better. So in summary, we use a green method, is using vitamin C. And we have loading the palladium, platinum nanoparticles on aerogel. That is new, because most report is on two-dimensional graphene nanosheet. And we find that this ratio gives the higher performance and higher stability. And so that's all. Thank you very much. Questions?
Do we have any questions for Dr. Hui? Sir? Here you go.
Just thinking, this work is more on reduction of platinum. The role of graphene remains same. I mean, if you can focus that graphene modification has done something, that is okay. But it is more to play with the platinum ratio.
Yes, yes. The ethanol oxidation reduction is mainly by platinum and palladium. The graphene aerogel simply increase the surface area, because from two-dimensional graphene sheets, they will aggregate together in most reports. And why we can have to file the patent, because we are the first one demonstrate on graphene aerogel. So we have a highly porous structure, and we utilize the non-toxic reducing agent to coat the catalyst. Thank you. Yes.
This might be a stupid question. I'm not familiar with the fuel cell.
Okay.
The fuel cell you talk about, you can use hydrogen and ethanol or methanol. Suppose the oxidation, if the oxidation of methanol or ethanol on the anode is not complete, okay, you have some left over, and that will go into expose to the air, right? That will run with water out to the air. If you're running a car, suppose. Have we considered about that, the ethanol or methanol pollution in the air, that problem? How do we solve that problem in the auto industry?
Okay, you mean not completely reactions?
That's right.
Yes, usually that question is good. I didn't think about this one, but usually this is like the system as I saw here is if not react, we'll go back. For example here, if not totally react, so this one and go through here. So, but for platinum-based, the reaction is really fast. Of course, some, if not react, what happens is they generate carbon monoxide, and this one will degrade the catalyst. So another thing we didn't do here, we are simply study the material performance. If you build a full device, so the ethanol will come from here, injection. So probably they will go back. It's like a full cell, falling. Okay, so yes, that is more detail in mechanical part. Yes, you are right. So you will fall here, and the water generate here. Yes, I understand what you mean, and so. That is one of the concerns, but in my team, we are simply working on material. I will bear in mind this one. Yeah, for mechanical department, they will make the full cell, yeah. Thank you.
Thank you very much, Doctor.
I
appreciate it. I think we're good. Any other questions? Thank you for your presentation.
Thank you very much.